Welcome to today's Happy Maths Hour.
It's all about using scrap paper in wonderful ways to make maths practical and to make it easier to learn.
And we're going to need some sticky tape, some string, some paper, some scissors, ruler, a pencil. What else, Tony?
Paper. So it's Caroline and I every Monday. Today's programme will include 4 different sets of activities. The first one is a tangram puzzle, and we'll show you how to make the pieces for the puzzle just by folding paper and cutting. The second one is just a few of the very many activities that we have put together for doing things with paper sticks. More about that later. And then there's a very rich trifold activity. Not that pudding trifle, this one is like, oh, it's as delicious as trifle, but here there are 3 folds and there's a huge amount of mathematics hidden in that simple little experiment, which we'll show you. And the last one is all about making an angle of 60 degrees very simply from just an ordinary piece of paper and then making an equilateral triangle. And investigating and explaining and proving why indeed the angle is 60 and the triangle is equilateral. So the first one is a chance to play and to be creative, and this puzzle has 7 pieces, and Caroline's going to show you how to make the puzzle, and then we're going to talk about some of the many things you can do with this puzzle. There you have the puzzle used in our logo for Maths Toys to make that little sailing boat. And Maths Toys is the YouTube channel. And here you have the square with the tangram puzzle in it and a symmetrical shape, which we'll discuss later. Now,
So
Caroline is going to take an ordinary piece of paper and she's going to do some folding. So you need to fold one corner to the, fold it right back so that the 2 edges go together and you make that into an angle of 45 degrees. And there you go. Those 2 edges should go together. The fold should go through the corner and crease it down along the fold. And the reason that we're doing that is to get a square. So Caroline needs to cut off that edge of the paper and she'll be left with a square when she opens it out.
I have found these days that not every child knows how to make a square from a piece of paper. And it works with any piece of paper, because all you have to do is then fold it over and that gives you a square. What's under there?
And now Caroline's opened out her piece of paper and she's got one diagonal in that square. Now the next thing is to find the center, but not to crease it down right across, but just to put the other 2 corners together and just to flatten it slightly in the middle there so she can mark the center. We need that center point. There we go. So she's making sure she knows exactly where the center is there. Opening it out now. Now she's going to take the bottom right-hand corner and fold it up to the center and crease that. Now that smaller triangle there is one of the triangles of our 7 pieces for the tangram. So Caroline's going to cut that off. Now the reason she didn't crease it across was she didn't want to crease the triangle that she's just taken off. So she's now going to go back and fold that, because now that's not going to matter anymore. Right?
We actually want this fold. This fold will be cut by the time we're done.
Yes. Now then, she's going to cut that long diagonal now, and those 2 pieces, those 2 triangles, there's going to be 5 triangles here. We've just taken off the one of the middle size. Caroline is now cutting the 2 larger triangles, and when she's cut them off, she's going to be left with a strip.
I
Well,
was so excited to discover you can actually make your own tangram. I couldn't believe it when Tony told me so simply and beautifully.
there you go. Now then, the strip. The first and obvious thing to do is to take the triangle, one of the triangles, fold the corner. Well, sorry, it's a trapezium, isn't it? But the one of the corners there, and fold it to the center, so you've got a triangle and a square on that side of the center, right? And Caroline's going to cut off that smaller triangle now and the square. Now she's left with another trapezium, but this time she's going to fold it so that she's got a parallelogram and a triangle.
So I'm actually going to fold through the square rather than make the square.
Yes. So you see she's now, the shape now, it looks is a parallelogram, and she's going to cut off that triangle, and she will have then the 7 pieces.
So here's my 7 pieces, 2 big triangles, 1 smaller one, 2 small ones, a square and a parallelogram. Found out I've now got to make that grey. It could be a kind of a fancy rocket as well, couldn't it? Or a fancy airplane. Right, so let's see. I'm going to use, I'm going to start off with what looks obvious to me is the 2 big wings. And then I think that there is a square. We'll make that, let's hope. And then perhaps, let's see, the parallelogram has to be making, oh look there, that's going to make a square there if I put that there. And will that, oh, that triangle's too big, so that must be this one down here. And now with these 2 remaining triangles that I have to make, is that going to work there? And then how do I make this last one? Is that, oh, yeah, I did it this time. I've done this a few times and I've struggled to do this bit, but what I love to see here is that these 2 triangles, which we kind of know because of the way we cut it, make a parallelogram, which I really liked.
So this is just one of hundreds, many hundreds of different forms that you can, creatures if you like, that you can make with the tangram pieces. It's an old Chinese puzzle, and there are many ways that you can play with it. Here are a couple more. You can see, because we've not presented it here as a puzzle, but actually drawn the pieces, so you can see where the 7 pieces fit. The little green man who's running along, and
even so, it is still quite taxing to even copying the picture. So it's a really good place to start by copying an existing picture, a picture with the outlines. It's a great place to start, just to get your head around it, see that it does actually work.
Yeah, so Caroline's made the hexagon there, and of course it isn't regular, the angles are different, but you can see the hexagon shape. Now, to go back to our grey shape, which we had before, we might ask you, what do you notice? We've talked about, well, maybe it's a bird or something that's flying anyway. We're both agreeing that those look like wings, but now let's get down to the mathematics, and what do we notice about the shapes? Now, if you're doing this with a group of children or a group of people, different people will notice different things. But what we use this one for very often is to talk about symmetry, and in particular symmetry by reflection in a line. Now, can you see there the line of symmetry through the tip of the nose of this flying creature?
Yeah, it's diagonal, isn't it?
Yes, yes, yes. Okay, so enjoy tangrams.
You can see it even just from the basic, just taking two triangles like that, you can see it that way. And that because it was different top and bottom, there wasn't, there's symmetry along that line, but there isn't symmetry along there. There isn't symmetry.
Symmetry is a very important idea in mathematics, but actually it's something that's very natural. If we just look at our own hands, we're carrying around with us these symmetrical things, our feet too, and we've got two eyes and two ears. We're quite symmetrical people, and most creatures are, and we see symmetry in flowers, we see symmetry all around us. So small children understand symmetry by experience, by just looking around. But it's a very important idea in mathematics, and it goes well beyond mathematics. It's used in crystallography, in physics, in particle physics. So
it's very much used in real life.
Yes.
And artists use symmetry.
Oh, absolutely. I mean, very many gardens and many buildings are designed to be symmetrical because that's sort of pleasing to people looking at it. It gives a pleasing appearance. Okay, so we're going to move on now to something else, but just showing you the link there. There's quite a few videos on our YouTube channel, and on the Aiming High website you'll find a lot of activities using all about puzzles, but getting maths out of puzzles, tangram puzzles. So the next thing we're talking about is paper sticks. Now, paper sticks came about, we invented the idea, I think, that nobody else came up with it first, because Caroline's a showman, aren't you, Caroline? And Caroline does the most wonderful maths shows, and she can entertain a whole hall of hundreds of people with maths. And that's quite an unusual thing to do. Most people don't think, first thing they think about when they think about maths is it's not a show, it's not for entertainment. But Caroline uses meter-long balloons, and then she shortens them sometimes, and she does a lot of, I say Caroline does, but she has children up on the stage with her, and they do wonderful things with balloons. And it's sort of mathematical, but the children don't feel it's maths, they feel it's just a lot of fun. So what we wanted to do was to have follow-up activities that teachers could do in lessons after Caroline's show, that they could then relate the maths that she'd been doing, the children had enjoyed, to the curriculum that they have to learn at school. And we wanted them to be able to do something with long, thin, well, in Caroline's case, she's using balloons. So we got this idea that you just take some old paper, it can be any newspaper or some scrap paper, you roll it very, very tightly into a stick, and then you've got a stick which is very versatile and can be used for a lot of different things. Now the one you see on the screen there is to make a meter stick to do measuring with. Before you start, you want to make your newspaper probably a bit longer than a meter. You really need two people to do it. It's very hard to do it tightly with one person, and 4 hands are better than 2. You roll it very tightly, use some sticky tape to secure it in your long thin stick, and then you take a short ruler and you mark 10 centimetre lengths along the meter stick, and then at one end you mark into 1 centimetre lengths, so you're ready for measurement. In a classroom, children can make their own meter sticks, so one between two, and then they're ready to measure. You can measure their heights. They can then draw graphs for the class, all the different heights. They can measure the classroom to draw plans or some different parts of the building and the playground or the football pitch and draw scale plans. Now, scale drawing is so important in life, isn't it? And to be able to read scale drawings is a really important skill, reading maps and building plans and using scale drawings in all sorts of design work.
Kitchens, decorating at home, planning a bedroom. There's just so many things. And even if you're making a big project, you need to be able to make a small version of it. Architects, of course, are the ultimate small scale drawing people. But as you say, roadmaps, so many. Write in the comments what things you can think of that need scale drawings.
Yes, I mean, the thing is, when you're maybe going to buy a new piece of furniture, will it fit in? You know, make a little scale drawing of your bedroom or wherever you're going to put this furniture and move the furniture around and see if it will fit. You know, see if you'll, not just if the furniture will fit, but will you be able to open the cupboard drawers and doors?
That's a very serious question. Is it actually going to be convenient? Open the cupboard, the drawers and the doors, and then get into it. It's all very practical.
Yes. Yes, a lot of ways to use scale drawings. And so that is a very good use for paper sticks. Now, we're going to go on to think about some puzzles. And Caroline's going to, actually there's two shown there, but we're going to show you three puzzles. Now we're going to move from 2 dimensions to 3. And
no, we're not. No, we're not. We're going to look at 2 dimensions.
All right. Okay, well, you'll see why Caroline says that in a minute. And we're going to show you a way of learning some more mathematics using our paper sticks. Okay, so over to you, Caroline.
Right, if you could stop sharing for a moment. Lovely, thank you. So what we have here is 2 triangles and 1 stick. So yes, they've got the string on them so that we can tie them together. The objective here is we've got 2 equilateral triangles and we've got 1 stick, and we need to make 4 equilateral triangles. So how are we going to do it? Let me see.
It's impossible, Caroline.
Well, no, I don't know. I'm going to give it a go. Let's see. We can put it there. Okay, we've got a slight problem here because a triangle is a polygon, which by definition is a closed 2D shape with straight edges. And these triangles don't close, they're open at the end. So, okay, so that won't work. What about bringing it there? Okay, now I've got 3 triangles, but they're not equilateral, and also they're not all the same size. What about going there? Well, I've got 2 triangles, but these shapes here, they're not even triangular. They've got 4 edges, they're quadrilaterals. What about going that way? Will that work? Okay, again, we've got the same problem. We've got 2 triangles and 2 quadrilaterals. Well, what if I'm going to give you a little bit of a helping hand here. What about now? Can you see a way if we now move into the 3rd dimension? Can we actually make this magic happen by using the 3rd dimension? And now let's see, how many triangles do we have? I'm going to use one I made earlier so that I can move it around more easily. We have 1, 2, 3. So that's those 3. 1, 2, 3. And underneath we have another one. And they are all the same length because I've used identical paper sticks. And I have 4 equilateral triangles, making.
Well, Caroline was trying to put you off the scent because I said we were going to be working in 2 and 3 dimensions, and and we are, aren't we, Caroline?
Well, we are. That's the solution is by going into 3 dimensions. But if you let the cat out of the bag too soon, the surprise is gone, and the realization of the power of going into the 3rd dimension.
And we want the whoever is doing this to be surprised by this. If they haven't seen it before, we want them to play an experiment with it and find out for themselves. So actually, Caroline's demonstrated it for you. But if she's got a live audience there, she gets people around up on the stage to assist her, and she doesn't do it herself. She doesn't show them. She gives them the balloons, and they join them together, and they have these balloons, and they how many is it? 6 balloons, and they make this tetrahedron, and they're often very surprised that they're able to do it.
Surprise is a very powerful tool when learning mathematics. It is something that you constantly experience when you're learning, and that is an important tool in getting a learner engaged in maths, and in knowing that every time they do an activity there is going to be a surprise and this really exciting moment where they work things out, not just once, multiple times. And so yeah, use surprise. Surprise is important. Don't let the cat out of the bag. Let the child experience their own surprise.
The other thing about these spatial puzzles is that visualization is a great help. Being able to imagine something and see it with as they say, the mind's eye, and practice helps to develop those visualization skills. So we're suggesting some really fun activities here with a serious intention behind them. And the next puzzle is
we're just going to go straight for it. We're not going to give you any clues. And what we have here is 3 squares. Now, they are made out of paper sticks, so they're not rigid squares. They have flexibility. But we are going to make a 3D shape using the 3 squares, and they still will be squares at the end of it. So what shape can you imagine, can you visualize making with 3 squares? Well, the most common, I should say, shape that people say is what's known as a triangular prism, like a Toblerone bar.
But you're not allowed to put 2 sticks together. Each edge should be just 1 stick.
Yeah, well, I didn't say that. So I just said a 3D shape. So that's fine. So yes, that didn't mention that yet. That is the rule. Every edge cannot be 2 sticks. Every edge must be just 1 stick. And you've got to use all 3 squares, and all 3 squares will still be shaped like a square. Well, you can let people have a go, have a nice go, and depending, but I'm going to just go straight to an aid for the solution. So I'm just going to use these. These are just cable ties, the kind that you get when you buy equipment, the one that curl round like that. So I'm going to give you a little bit of a clue here, so I can demonstrate this. You can see it from different angles.
Caroline will have some children up on the stage, each one holding a square, or maybe 2 people for each square, huge squares, and she will get them to try to make this shape. And at this point, they will be holding it up with those 2 squares linked together at 2 opposite vertices there. And the idea is now to use the green one, the other one. What
do you do with it? Where does it go? And I can hear some of you screaming, put it through the middle. Well, when I'm doing the show, I actually then go do this, put it through the middle. So language is also important. That's to demonstrate how important language is. And yes, that is a 3D shape, but it's not a 3D shape made up of squares. The faces, well, the faces are not polygons. In fact, there are no polygonal faces at all on there. So we actually need to make a shape, and I'll give you a clue. We need to make a shape made up of triangles. They will all be equilateral triangles. And the way that you do it, we can do it through the middle. I'll do it over the top. I'll use my little ties here. Tony, would you like to talk about it while I just tie them up?
Absolutely, yes. So what we're going to end up is a shape with triangular faces. At each vertex, we're going to have 4 edges, and
I'm
we've
going to
got
cheat.
12 edges.
Here's one I prepared earlier.
Yes, there you are. And now you can also see, I think, why we chose, well, I hope you can, you can see why we chose to make the squares, each square a different colour. So you see a yellow square there, a red square, and a blue square, turquoise coloured blue square. And we're back to symmetry, aren't we, Caroline?
We certainly are. If I stick my hand through there, or if I maybe use a card so you can see it, that this is your mirror. Look at it from this face or from that face, assuming that the card goes right through that middle square. The amount of triangles are identical on both faces. So when I ask people to tell me how many faces a shape has, if you start counting 1, 2, 3, 4, 5, 6, wait a minute, have I counted that one? 9, 10, I don't know how many faces there are. But if you just count on this face, on this from this way around, 1, 2, 3, 4, you can see that the opposite end has the same amount. So and there are no more. That's all there is.
Then. And what you can see is the card that Caroline's showing you. In fact, she's really just trying to indicate that yellow square is what we call a plane of symmetry. It's like a mirror, a flat mirror, and the other 2 planes, so the red plane equally is a plane of symmetry. And the blue plane, again, that's also a plane of symmetry. So we talked about with the grey tangram shape, that was all in the 2D, and now we're looking at symmetry in 3 dimensions. Also, we've got here what we call a regular shape. And what we mean by regular is everything's the same. All the faces are the same shape. They're all equilateral triangles. All the angles are the same. They're all 60 degrees. Well, the angles in the faces are 60 degrees, and all the lengths of the edges are the same. And that is one of the famous Platonic solids described by Plato, who actually established that there were only 5 of these. They're all common shapes, or pretty well known shapes, and this is the one, the octahedron.
And the other thing is that every vertex has the same number of identical faces coming off it. So every single vertex has 4 triangles, and only 4 triangles, no more, no less.
So Caroline's going to show us another puzzle here, and here she's starting with 12 edges again, 12 little sticks, each of which is going to form the edge of her shape. But it's going to be another octagon.
Yeah, another octahedron. We're making this shape. So this time
Octahedron,
I'm
yes,
not revealing.
said the wrong thing.
It's fine. Oh, yeah, octagon, for anybody that's forgotten from when you went to school, octagon is a 2D polygon, and octahedron, which I never learned, is the 3D way of referring to a 3D shape that's made up of polygons. So the thing with this is that this is a closed loop. There is no opening, and you can't, this puzzle must be made by using a closed loop. Now, you can use elastic if you want, it might make it a little bit easier, but I'm using just recycled materials, so string, sticky tape, and an Aldi magazine. So what I'm going to do is I'm going to start with, this is the shape we want to make. I'm going to start by making triangles. That makes sense, doesn't it? So I've got one triangle, two triangles. Oh, if I didn't loop that quite enough times. Here we go. This is much easier with balloons, by the way, believe it or not, it's a lot easier with balloons. Three triangles, and I've got four triangles. Oh, well, I've got four triangles, but again, we're in 2 dimensions. This is flat on the table. I've got 4 triangles. Well, can we go from having 4 triangles to having 8 triangles without adding any more sticks, without adding anything? Well, you might have to add some string to hold the vertices together. But what do we know? We need to make sure that every vertex has 4 edges or 4 triangles on it, and not more and not less. And we need to have the 4 squares, the 3 squares, I should say. We know it's 3 because we made it this way. So you can, you can start putting them together like this. We're going to make a triangle there and a triangle. Oh dear. Wait a minute. We can't join those together because we don't have 4 edges or 4 triangles. We've got 6 edges. Well, that's a clue for us. We have 1, 2, 3, 4 triangles, but we've also got gaps here, and we definitely got 6 edges. So we know we're not on the right track there. So that's not it. Well, we had a clue here. We made this up as squares. So let's see what happens if we make squares. Oh, that's interesting.
This is looking hopeful.
Definitely. Oops, let's see if we can see the whole thing. It's definitely looking hopeful. Now, how are we going to go from, we're going to visualize how to go from this to this. Well, let me bring 2 of them together. I bring 2 of them together.
Ooh, we're halfway there, Caroline.
I think so. I think we are. If only my fingers were invisible, that would be so helpful. See if we use a green screen to make my fingers invisible. And now if I bring the top 2 together and the bottom 2 together, all I need now is some extra hands.
Exactly.
Extra hands and invisible hands so that you can see.
That's so pretty. Yes. And of course you can do it with longer sticks, and if you've got 2 people together, it is easier. But the 4 triangles around the square is your clue, and then 2 triangles going up from the square, and 2 triangles going down from the square, and you've got your octahedron.
The reason why I made it so small is so that you can see it on the visualizer. Is definitely easier to do if you're using longer sticks.
That's a great puzzle. I really like that one, Caroline. And there's a lot of mathematics there to talk about, to learn for the children, actually, not for the teacher to tell the children about, but for the children to discover for themselves.
And have lots of surprises and lots of victory moments where they're working things out and making discoveries.
And we've got the tetrahedron, tetra being 4 and hedron being faces, that we made, and the octahedron, octa being 8 and hedron being the word for, again, the word for face.
The way I present that is tetra meaning 4, faces. So tetrahedron for faces. You're learning ancient Greek here, and octahedron, and it's a reminder that octa means 8, hedron means faces.
Okay, so, and there's many more ideas on the Aiming High website for activities with paper sticks, wonderful versatile paper sticks.
I'm just going to mention the bendy quad. It's a fantastic activity. You make a cube out of sticks, and there's so much you can do with it. So definitely look up the bendy quads one.
Bendy cube, and there's a bendy quad as well.
Oh, sorry, bendy quad. There's a bendy quad. That's right. And this is the bendy cube. Thank you. It's a bendy hex.
Oh, and okay, so paper folding, we're going to get into some paper folding now, folding triangles, but Caroline really is quite a lot involved with early years. This is preschool activities for children to play with shapes, not seriously being taught mathematics in any way, but just playing with shapes, talking about what they see, what they're doing, having fun, and building the basis for later mathematical learning. So
yeah, so they literally for early years just get lots of triangles.
So you'd say to the children, fold a triangle, see what you can make, and then as they make different shapes, you don't necessarily tell them anything. You just ask a question. You say, "Oh, you've made a triangle. You've made 2 triangles there. You've made, what's that shape? Oh my goodness, isn't that an interesting shape?" And talk about the different things the children's actually doing, and only as long as they're interested, not continue if they get bored and want to turn their attention to something else. Leave it, maybe they'll come back to it another day. So what we like to do is to talk about learning at home, helping parents, not just with very small children, but especially with the lockdown and children not being in school, children of different ages in the same household. So we introduce starter activity that everybody can do together, and then different activities for different age groups. In a minute, we're going to talk about the trifold activity and start with everybody doing something together, and then the very small children can do this playing with triangles, and older children can get involved with more activities with trifold.
While the older learners are doing trifold, the younger learners can copy. So they love to copy, and they can do whatever version of trifold that they come up with for themselves. And it's all good because it's all exploration.
Now here, there's an enormous amount of maths geometry in this one activity, and all you need is a piece of paper. It's great, and I'm going to tell Caroline what to do step by step, and she is going to follow this activity. Okay, so first of all, Caroline's got her triangle. Any triangle will do, it doesn't matter what shape it is. And she's going to mark.
It's not, that's a right angle triangle. I just want to make absolutely clear. It's any old triangle.
Well, it could be right angle, but the point is that it works whatever the triangle is, and we're just showing you with not a special triangle, but just any old triangle. And if your learners do it, let them all make their own triangle to start with, and so everybody in the class will have a triangle with different angles. Now, Karen's going to mark A, B, and C at the 3 vertices.
A, B, and C. Are those big enough? Can you see them?
That's beautiful, Caroline. Now Caroline's going to make a fold through the top vertex A, and the fold line is going to be down to the base and at right angles to the base. Now, to make sure it's a right angle, she's going to fold the point C across so that C will be still on the baseline, and the fold is going to go through A. So she makes that fold.
This is the hardest fold to do because the A must remain a vertex.
It's got the fold has got to go right exactly and precisely through the vertex there. Yes.
And it is definitely the hardest one to do. I think I've got it.
Actually, the more obtuse the angle, the easier that fold. Okay, so brilliant. So now the line, Caroline, if you dot it so that we can see it, the fold line is a line that's perpendicular, that means right angles, to the baseline BC.
When Tony said the more obtuse it is, what it means, if that angle was more open, it would have been a much easier fold there.
Bigger, yes, bigger angle.
Yeah.
So now the on the base there, that point is called R. So if you like to write R there to remind ourselves when we talk about R, that's the point we mean.
Shall I mark that they are right angles?
Yeah, yes, you can do. Yes. Okay. So now fold the point A down to just the vertex just on the point R and make a crease there. Now, it looks as if the fold line that Caroline is making is actually parallel to the base. Now, we can't assume anything, but in fact, it is. It is parallel to the base, and that's something that is quite easy to prove formally in the geometry.
It's only parallel to the base because we started off with a line that is perpendicular to the base, which is why that positioning of point R is so important.
Absolutely. Now, Caroline's now going to fold the point B across to R, as she did with A, but this looks a little bit different. So there.
Again, a little tip to help you. I'm using really thick markers so that you can see what I'm doing. Use a nice thin pencil, because right now I'm working out where exactly point R is, and it's not very precise because I'm using a thick marker, and that's not, anyway, it'll do for the demonstration, but see if you can do. Now, younger learners, it'll make it quite higgledy-piggledy, but they'll still get the benefit from it.
Okay, now do the same with C, Caroline. Bring C over to R as well. And so the vertex C has got to go as exactly onto the point R as you can make it, and crease that edge. And bring the flap A down again. And now, wow, that's very neat and tidy, isn't it? And it appears that Caroline, she's turned it over so that it holds in place. The shape that she's made by folding those three flaps down is a rectangle. And wow, there's a lot we can deduce from that. Now turn it over again, Caroline, and see those three flaps coming together at that point at the bottom. Those angles, A, B, and C, from the original triangle.
I mark them on the back.
A, B, and C. And they fit so beautifully together, it looks as if it's pretty convincing that the angles add up to 180 degrees. Now, there you go. They've got a straight edge there, so you can see the angle on the straight edge is 180, and the three angles add up to 180. Now, you can do that in primary school, And that's enough of a proof for younger children up to the age of 11, 12. By the time they're 13, 14, we want to begin to investigate the congruent triangles, congruent meaning exactly the same, and they are the same if they fold on top of each other. Now, the little rectangle that Caroline's holding shows us that the area of this rectangle, we can easily work that out. Now open it up, Caroline. Now the triangle is covered twice when we fold the flaps in. So the area of the rectangle is half the area of the triangle.
Oh my goodness. So these three external triangles added together have the same area as the rectangle that they make. And there's a rectangle on top made out of triangles and a rectangle underneath that's just what's left of the original triangle.
Yes. Now, because we can easily work out the area of the rectangle, and because we've got these pairs of triangles that are the same as each other because they fold on top of each other, and the mathematical word for that is that they're congruent triangles, we've got an easy way to prove that the area of the triangle is half the base times the height. Now, we won't go into that in detail now, but I think everybody can imagine that we can use that rectangle to prove that formula. So not only have we got a formula for the angles of the triangle adding up to 180, we've got a formula, we've got a way for, we've got a proof of that, and we've got a way to prove the area of the triangle is a half the base times the height. What we've also got is pairs of triangles that are the same, and the same in the mathematical word is congruent. But we've also got, we were just talking about it earlier, we've also got more symmetry here. So there's a lot that we can use this simple paper folding exercise for in talking about congruent triangles, similar triangles, and symmetry.
So I don't see any symmetry at all in this triangle.
Well, Caroline, perhaps you would like to fold over one of those flaps with with the angle B on it. Now draw along that edge so that we can mark out that. That's the edge I meant, yes. Now bring the corner C.
Well, I've just seen something. Okay.
Now do the same thing from, yes, them there.
That's what you're talking about with the congruent triangles.
I am. Right. Now, what we like to do is to colour this as well. So each pair of congruent triangles is coloured with the same colour. So we've got 3 pairs of congruent triangles there.
Wow. You could also draw in the vertical lines to show the lines of symmetry on those.
You've got lots of lines of symmetry.
But of course, this is a triangle here. That's a triangle. This is not a triangle. This is a quadrilateral. But the 2 congruent triangles are symmetrical along that line of symmetry.
So you've got a lot of symmetry there. You've got a lot you can do about congruent triangles. You've also got similar triangles.
That's similar to the big triangle because the angles are all the same. It's a smaller version of the big triangle.
So there's a lot about similar triangles too, and that leads us into, for the older children, the 16 to 18-year-olds, into another theorem in geometry which they have to prove, and the easiest proof of the theorem, which is about a triangle, it's called the ratio theorem, and the easiest proof is using the similar triangles that top flap, the triangle with vertex A, is similar to the bigger triangle. And okay, we'll leave it there, but there's It's a huge amount of geometry. So all the geometry is convincing when you have the paper folding exercise and you talk about it, but then you can easily, if you have to, turn it into a formal language of geometry and write a formal proof based on the paper folding. So it's a lovely exercise which has ideas, and it relates to different geometry that's taught to different age groups in school.
I'm completely blown away by how much there is in. All I've done is make 3 folds, no, 4 folds, 1 there and 3 others, and there's so much in there. And then it's fantastic.
Yeah.
What's next, Tony?
Oh, well, the next thing we're going to do, we're going to say goodbye to trifold for now, and go back to it, please, and have a look on the Aiming High website for our learning pack with lots and lots of ideas about trifold. And now we're going to move on to paper folding to get an angle of 60 degrees. And all we need is an ordinary piece of A4 paper. Caroline is going to fold this lengthways in half. And then make a crease and open it out. Then she's going to take the bottom left-hand corner and she's going to make a fold that goes through the bottom right-hand corner. So the corner that was at the bottom left hand is going to go on the middle crease, and again she's got to be quite careful to go exactly through that bottom right-hand corner, and when she's got it in the right position she's going to make that crease. And it's marvellous, but the angle that she's made is 60 degrees. Isn't that amazing?
Seriously? 60 degrees?
That's 60 degrees, yeah.
Okay.
Wasn't that easy? Now we'll make an equilateral triangle, and then we'll talk about why it's 60 degrees. So now Caroline's going to take the top corner on the left and fold that down, making the fold along the edge. Yes, the edge. Show them, Caroline. It's where the paper was folded up, along that edge. Fold this paper down, and okay.
And this edge wants to follow the what is now the base of that triangle. This edge wants to go on the first fold that we made.
Yes, and it's almost there. Turn it over, Caroline. You'll see that you've got an equilateral triangle with just a little flap, which is going to just tuck in and get rid of.
You can cut it off if you want, but there's no need. You can just tuck it in and it's gone.
And that is now a perfect equilateral triangle. And
yeah, okay, yeah. And my mother's name is, seriously, Tony, a perfect equilateral triangle. All I've done is make 2 folds and
it's amazing, isn't it? And even more amazing is that you can now easily fold each of those vertices to the opposite edge carefully, and then lift them up and make a tetrahedron from it.
So right, okay, let's do that then.
Each vertex goes to the opposite edge.
Oh, now I tell you what I've got a nice line here from that the original fold where I folded the paper in half. I'm going to use that line, and that's my fold line for the first one, so that I get it in the right place.
So we're going to get 4 triangles folded on top of each other.
I'm again, such a simple activity. Look at this. They're all the same size. All 4 triangles are all the same size, and they fold over onto each other. beautifully. And you said that will make a tetrahedron.
Yes, all you need is some sticky tape now.
Woohoo!
You've got your tetrahedron. Isn't that beautiful?
It's beautiful. And all the edges, this is a regular tetrahedron, all the edges, that's a tetrahedron, 4 faces, and all the edges are the same length, all the faces are the same size. Every vertex has the same number of triangles, which means that it's a platonic solid. It's a regular
And the
polyhedron.
beauty of this is it's so easy to do.
It's really easy.
So unfold it, Caroline, because now we've really got to look at it a bit more critically. I think we're all convinced that it's angles of 60 and it's equilateral triangles, but let's open it right out. Okay.
Oh, it makes a pretty pattern.
Yes. Okay. Now just make that first fold. Well, the first fold was the lengthwise one. That's the fold I mean.
I'm going to fold it the other way so that now we've got plain paper. Might help if I have to write something on it. Okay, go ahead.
At what is now on the bottom left-hand corner, you have got obviously 3 angles there. Now, 2 of them are on top of each other, aren't they?
Yes. So we know that whatever that angle is, the one underneath is identical because we've got that. Was it a similar triangle? No, what was it? One of this identical congruent triangle. So I'm making a congruent triangle by placing this triangle on top, and whatever's underneath is identical, obviously.
Yes. Now, Caroline, make another fold that goes through that corner, so that you have got 3 triangles on top of each other.
Oh, okay, like I did with the tetrahedron. Here we go.
Yes. Now those, the corner there that Caroline's showing us, we have got 3 angles on top of each other, and they're all the same. All right. Now open it out, Caroline. And so each of the angles, and in fact, Caroline, could you draw the line on the paper to show us?
Yes, I'm just turning it over so we can see it a bit better.
Yes, just a dotted line.
Remember what I said, that this pen is a thick pen, so use a pencil yourselves. You can see it more, it's much more precise. It's hard to see. Here we go. Whoops. Okay, you're telling me that, well, we knew that 2 of those angles were the same because they must all be the same because we folded them over onto each other and they were just sitting on top of each other.
And they add up to
well, we know that's 90 degrees because I used a standard piece of paper. So, and they're all the same. So it's 90 divided by 3.
30 degrees.
30 degrees each.
And then the 2 of them make the 60, which is what we were claiming.
Which was what our original claim, which is, make sure I get the right one here, that one. So it's this here is 60 degrees. That was our original 60 degrees, which is what you said it was. So each one of these is 30. Yes,
and of course, this is, as we said, it's not a lesson, so we're not going to go on about this any longer. But
no, but it's super exciting that all you're doing is folding paper, and hey presto, you just have to have a few basic things like know that a right angle is 90 degrees and things like that.
Yes, lovely. And you can obviously get into ideas like congruent triangles and prove that you have got the condition for congruency, which is one of the things they teach about in school, and children have got to be able to write it down in the right way. But it's so easy with the paper that it'll be clear to anybody who does it this way what is happening, and that this proof is a nice easy proof. So that's another very rich activity. Now go to the Aiming High website and you'll find the Making 60 activity will give lots of suggestions for teachers using this activity. It's a simple activity, it makes maths fun, it makes geometry easy. So you see there the illustrations of what Caroline did with just an ordinary sheet of paper and making an equilateral triangle, then making a tetrahedron, and then proving some geometry facts just using paper folding and reasoning about showing congruent triangles and reasoning about the angles in the triangles.
I would agree. It's very enjoyable. I love that. Thank you.
Now, this picture shows you a little bit about AIMSEC and why I am involved and have been for a while with working in South Africa and other African countries, because I think that education is the most powerful weapon which you can use to change the world. That's what Nelson Mandela said. And there you'll see at the bottom a picture of him reading with some children. And I want to change children's lives, but I can't do it. So I work with hundreds of teachers, and they are the important people. They're changing the lives of those children who, with a better education, should have better life chances and opportunities for a better life. And you see some of the classes there, the top right hand, you see that enormous class. That's very common that teachers are working with huge classes there. And just on the top, just to the right of centre, you'll see a village street there. Now that's where I live and where Caroline's father lives, in Fishhook on the Cape Peninsula. When I say it's where we live, it's part of Fishhook. Actually, I don't live on that street, but it's where I live is only about 20-25 minutes, maybe half an hour at most, to walk from my part of Fishhook to that part of Fishhook. And that's where it's so awful, the poverty and the difference in the comfortable standard of living I enjoy, and for those people having to go with their pot on their heads, those ladies, to collect water because there isn't water in their house, there's several families sharing one tap. So that's life in South Africa. And there you see other pictures of children in school, and one picture on the top left of AIMSEC working with teachers. That's what we do to empower teachers to make education better for the children. So it's time to say goodbye. It's been Happy Maths Hour. We enjoy maths. We enjoy it together, don't we, Caroline? And we like to make it enjoyable for the teachers we work with and to empower them to make maths enjoyable for the children.
And for families at home.
Absolutely.
Thank you so much. We're on every Monday, London time, from 5 till 6. Please join us every week. And of course, on the YouTube channel, which is the Maths Toys YouTube channel.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.